Okay, welcome. I'm now recording the session. We're missing one person, but I don't think he's going to be joining us. He told me that he had another commitment, and so I'll be recording it for his benefit. And also, the rest of you, it's for your benefit as well. We're going to go over a whole lot of material really fast. And so don't feel bad if it doesn't all sink in the very first time around. It is all being recorded, and so you'll be able to go back and you'll be able to watch the recording. So let me just start off by saying welcome. I am Doug Hendricks. I'm the Celestial Navigation Instructor for Bonneville School of Sailing and Seamanship. Let me tell you a little bit about myself and then give you a little bit of time to tell us about you. Here comes the other person. Excellent. Hang on a sec. Let me let him in. Okay. So hello, Andrew. All right.
Hello.
Hi. So we're just going to go over some quick introductions first, and then we'll dive right into it. Okay, so I'm Doug Hendricks. I have been sailing for over 35 years, much of that out on the ocean. When I was in my 40s, I took early retirement, and I used to work in Silicon Valley. I was a physicist slash engineer, made computer chips and things, and things worked out pretty well for me. So I took an early retirement, and for the last 17 years or so, I've been spending 9 months of every year teaching physics and engineering, and the other 3 months of the year I've been out on the ocean sailing, which works out really well, because if you want to sail across an ocean, you can't do that in a 2 or 3 week vacation. You need a 2 or 3 month vacation to do that. And I also took off 1 year and just lived on my boat for 1 full year and just went all over the place. And it was glorious, glorious. So I sailed across a lot of oceans, navigating by the stars. I told the other people on the boat, I says, if you want to use the GPS for your own benefit, that's fine, but you got to keep it secret. Don't tell me what the positions are, because I'm going to navigate by the stars. And it was a lot of fun. I really enjoyed that. So I started off sailing in the San Francisco Bay Area, that Silicon Valley, that's where I used to work. And that's pretty much Mecca for sailing. It's just wonderful sailing. And then after that, I've been all over the place, pretty much all the oceans and all over. Okay, so that's a little bit about me. So if you guys could just take a minute or two and give us a Twitter version of introduction to yourselves. I'm specifically interested in knowing how much sailing experience you've got. I've already talked via email individually with you, so I've got a reasonably good idea about how much celestial navigation you guys have got, which for pretty much all of you is very close to zero, and that's okay. That's all right. But I would like to know what sailing have you done? What sailing do you hope to do? And also, how much astronomy do you know? How many constellations could you point to and identify? So how about, let's go with Alex. You want to go first?
Yeah, sure. So my name is Alex. I live in Utah, near Utah Lake, and my sailing is pretty limited. I'm mostly just a hobbyist, and I sailed as a scout and loved it. Forgot about it when I was an adult, but then always thought it was pretty cool. Then sailed once in Carlsbad, or I guess San Diego, and then reawakened my love of sailing. So I joined the Utah Lake Yacht Club here nearby, just a bunch of hobbyists with a bunch of old broken up boats, making the best of it. And I just got really involved doing mostly small boat sailing and some slightly bigger stuff. But as far as astronomy, celestial related things, I'm only in the last year or so have I gotten a lot more interested in kind of archaeoastronomy and other astronomical events. And I've, got a nice telescope and some charts and have been kind of teaching myself, but I don't have any formal kind of training. And so that's why I jumped at this opportunity to jump in. I'm also a super nerd. I would go to school the rest of my life if I could support my family while doing that. So I'll absorb anything like a sponge. So thank you.
Sounds good. Now tell me, what is archaeoastrology?
So archaeoastronomy is kind
Astronomy,
of,
sorry.
yeah, it's a study of what did ancient peoples believe about the stars and just the cosmos, the heavens, what they told us, what things meant. A lot of it is scientific. It kind of there's a border between scientific and kind of religious, philosophical, but I think all of it's really interesting, and it made me start looking up rather than down at a smartphone for the first time in a long time, and has made me very curious. So
Okay, very nice. Paul, would you be willing to go next?
I've sailed mostly on Utah Lake and mostly just in a couple of Todd's classes, so I don't have a whole lot of experience in sailing. But I was going to take one more this summer. And then this class is mainly because I'm kind of curious about how the old sailors used to do things back in sailing ship days. I don't have a whole lot of math facility, but hopefully that won't slow me down too much. And for astronomy, I'm probably one of the more leading experts in the state on finding the Big Dipper. I can do that real well.
All right, good. That's where most people start. Okay, Andrew, how about you?
So I have minimal sailing experience. I sailed, I think, a few times as a scout. I sailed on the Charles River in Boston. I've maybe sailed around or near Catalina. There was a Boy Scout camp out there. I may have sailed out there. It's been a long time. Astronomy, I may have taken astronomy classes as a scout. I can name a few constellations, not maybe several. That's about it. Nothing extensive. So minimal sailing experience. I'm actually sailing from Hawaii to California in June.
Oh, great.
And I'm trying to add some expertise to my resume to help out. Not that we'll be doing it, but I think it's a unique skill to have. I think it's a lost skill. I went to the Polynesian Cultural Center on Oahu a few years ago, and just kind of gotten interested in how they used to navigate just by the stars only. Obviously, we have all this, compasses and GPS nowadays, but yeah.
Yeah, the way that the Polynesians did it is just, I'm in awe of how they did it. That's amazing. Keith, are you able to communicate with us while you're driving? He might not be. Keith is in a car. And so, yeah, we'll skip Keith and come back to it. Okay. And now, as I understand it, you all have Mark III sextants now, or will soon. Does anybody have anything other than a Mark III? Okay. Oh, nice. Okay. All right. Very good. Okay. All right. So let me share my screen with you, and let's move into the good stuff here. Okay. So, whoops, not that. Let's go to here. All right. So the agenda for today is we're going to go over some basic non-celestial navigation, like how to triangulate your fix, which some of you told me that you have done, but not all of you. And so hang on, my computer is doing one thing a little funny. Okay. All right. So yeah, just you need to know how to navigate on land before you can navigate by the stars. So we'll go over that. Talk a little bit about sextants, but not much, because I think we've already done a lot of that via email ahead of time. Identifying the stars is critically important. You can't do much with the sextant unless you know what star you're measuring. So identifying the stars and the planets are going to be real important. We'll talk about that for quite a bit. And then we're going to talk about how to use the smartphone app. The goal for tonight is that when we wrap this class up 2 hours from now, I want you guys to be able to go outside, measure a star, not using a sextant, but using a very, very simple tool like this. Okay. We're just going to take a protractor with a weighted string, and this is the tool we're going to use to measure the stars. Really, really simple and easy. So you're going to go out and you're going to measure a bunch of stars, and you're going to know how to use the smartphone app to be able to put the numbers into there, and then figure out your position. So it looks like Keith is back with us now. Okay. Let me pause for just a second here. So Keith, is that you? Wayland Pros?
Yeah, wireless land professionals.
Ah, okay,
Sorry,
all right.
got home now. Much like the others, I actually taught sailing in college on on lasers, and then it's been 40 years since then, and I haven't sailed. But I'm signed up to take 3 of Todd's classes this summer, and this was the first class up, and been interested in navigation since learning about John Harrison's clocks that help make navigation work. So I'm also a techie guy. I do wireless lands. So that's me. Sorry to be late.
Not a problem, not a problem. Yeah, we're just now getting into the meat of things. Okay, so the agenda for today is this. We are not going to learn how to use the sextant today. That will come in next time, but we're going to learn how does celestial navigation work? How could you go outside with a protractor, measure a couple stars, put the numbers into a smartphone, and figure out what your position is? So you'll understand how celestial navigation works. Now, let's see here. Okay, then there are 3 more class sessions after today. And so in session 2, that's where we'll learn how to use the sextant and all the corrections that are needed, and there's a lot. We'll learn how to use the nautical almanac, how, all the things that you see listed here. We'll do noon sun shots, we'll do Polaris shots, but that's all coming later. So we've pretty much done the basic survey here. Most of you tell me that you are brand new to celestial navigation, have not used the sextant before. Some of you have some good knowledge about astronomy, so hopefully that'll go fast. In your feedback to me, you said that several of you have done orienteering as a scout, but not so much sailing type navigation. There's a lot of overlap there, so that'll go easy. And then in your background, when we talked via email, most of you said that you have had trig at some point, but it's been quite a while, so a review wouldn't hurt. And now, as far as the mathematics, that's the part of the class where I'm going to be very flexible. We can go deep into math if you want, or not so deep into math if you don't want. We'll see how it goes as the day gets there. Okay, so first, I trust this is review for everybody, but we got to be 100% rock solid on this. A lot of people get latitude and longitude mixed up. They know that one of them tells you how far north or south you are of the equator, and one of them tells you how far east-west you are of the prime meridian, but people get them mixed up a little bit. So make sure you guys are clear. Latitude is the one that tells you how far north or south you are of the equator. Longitude is the one that tells you how far east or west you are of the prime meridian. Okay, so if we want to know what the coordinates of this point are right here, okay, let me turn on my annotation. All right, so let's do the latitude first. Okay, so here's the equator, and you can see that we're basically 20 degrees north of the equator, plus or minus a little bit. And then each one of these lines here is each one of the vertical lines here is 20. So this is 0, 20, 40, 60, and so forth. This one here would be 180. So this 160. So this position here is a little bit less than 160 degrees longitude, and a little bit more than 20 degrees latitude. And turns out that is, of course, Hawaii. So 21 degrees north, 157 west, depending on which island you're talking about. Okay, so I'd like you guys to take a minute and find the place that is located at 40 degrees north latitude and 116 degrees east longitude. And so it's near a letter. One of the letters of the alphabet is really close. It's not exactly on the letter, but it's really close to the letter. Anybody want to take a stab at telling me where this is?
How about N
In?
in North America?
Okay, North America, okay. Well, the 116
Oh, I
degrees
went
is
west.
east,
My
not west.
mistake.
Okay.
Yep.
Yeah, so
That's
we
my
got to
mistake.
go east of the prime meridian. So we're going to be over in somewhere in the Asia.
A or S? Yeah,
Okay.
S.
Okay. Yeah, on a map of this scale, it's hard to be sure, but yeah, it's over by the last A in Asia, and so that would be Beijing, China there. All right, so hopefully you're all good on latitude and longitude, and also hopefully you guys understand that if we want to do better than just the nearest degree, what we do is we break up the degrees into minutes, much like a clock. You know, we don't say that it's 13.7 degrees. We say it's 13 degrees and 53 minutes or 47 minutes. So where there's 60 minutes in 1 degree. And so that's the way it's generally done there. Okay, let's go back into here. Okay, now nautical charts. This is something that you need to be familiar with in order to do celestial navigation. You got to start with terrestrial navigation. So what you're seeing right now is a very small version of this. So this is the real nautical chart here. You can see they're quite large. And so this is the waters off the coast of San Francisco. So if we were out here sailing, we would be plotting our position on the paper here. Right, so there's a wealth of information to be had in the nautical chart, and you need to know that. So let's talk about some of the things you can get from the nautical chart. Okay, so along the sides of the nautical chart are the latitude and the longitude markers. So like along here, so let's suppose that we are located right here. So if we go to this side right here and then read whatever number you see there, that'll tell us what our latitude is. And then if we go either up to the top of the chart or down to the bottom, oh, and by the way, we can go to the right too if we want. And we can go either to the top of the chart or the bottom of the chart, and that'll tell us what our longitude is. I have to turn off annotation before I can go to the next slide. Okay, so as far as directions go, every chart has a compass rose on it, and big charts will usually have several. So here's a compass rose down here. There's another compass rose up here. And the compass rose, there's the outer ring. Let's see, I think I put a slide in here where I had it enlarged here. Okay, well, I'll come back later and talk about the compass rose. I have another slide later in here. Okay, so dead reckoning is how we know approximately where we are. And this is important because the method that we're going to use in celestial navigation, it requires that you have to have at least a rough idea where you are. It is possible to do it another way, but almost nobody does it that way. The mathematics is a lot more complicated the other way. The simplest way, where you don't have to do as much mathematics, is you have to have an assumed position for where you think you are. Even if that position isn't completely right, that's okay. It just needs to be a starting point. And so you're going to get that assumed position from what's called deduced reckoning, or generally called dead reckoning. And so the way that dead reckoning works is you start off at a known location. So let's say, so this is Santa Cruz, California. Let's say you leave the Santa Cruz harbor and then you head out and you go on a compass heading of 265, and the M stands for magnetic. So that's why I know that it's a compass heading rather than a true heading. So, so you guys know if you've got a compass, north is 0 or 360, east is 90, south is 180, and west is 270. All right, so if we go on a heading of 265, then we're going a little bit south of west. And so, at least according to the compass. Now, our true direction is going to be different. We'll talk about that in just a minute. So we're going to keep track of that that direction, and we're going to sail for a couple hours. And the boat has an odometer called a log, and it keeps track of how far you've gone. So let's say that we've been for a couple hours. We've been sailing at a constant heading of 265. And our odometer tells us we've gone 32.8 miles. And then we, at 9:21 in the morning, that's when we tack or return for whatever reason. And so now we go on a new heading, and our new heading is 340. And we go for 39.5 miles there. And so now at 11:38, we now turn again. And so we go on this new heading for this new amount of time. Okay, so at 14:05, this is where we are, right? What do you guys think? Do you guys think that that's where we are? Anybody want to suspect that maybe we won't be there? What's the reason why we might not actually be where we think we are?
Currents, drifts.
Currents, definitely. You've got currents running there. Actually, there's a whole bunch of things that could throw you off. Okay, so the heading error, for one, like you tell the helmsman to steer 265, but if you're out on the ocean and you got these big swells, the boat is getting pushed one way and then pushed the other way, and so even if you got a really good helmsman, it's really hard to keep it exactly on 265. Current is one that you mentioned, and currents can be very strong. Off the coast of Northern California, there's a current that runs along here called the California Current, which is a pretty good current. It's definitely not negligible. It can be anywhere from 1 to 2 knots of current, which could throw you off by a long ways. So that's one thing, but there's more. There's also leeway. Especially if you're sailing, if you're motoring, you have a little bit of leeway, but not so much. But if you're sailing, you can have a lot of leeway, especially if you're on a beam reach. So where the wind is coming off, directly off your beam, like 90 degrees. You can be, depending on what kind of a keel you have, you could be slipping downwind quite a bit and not knowing it. So you got to be careful with dead reckoning. If you're keeping track on a chart, you think you're here, but you could actually be here or here, or you could be off by quite a long ways. Now, for celestial navigation purposes, that's okay, as long as your assumed position is somewhat reasonably close to your real position. I mean, it can be off by 100 miles, and that's okay. It'll still work for celestial navigation. But you do have to have an assumed position. Okay, so doing it graphically is the way that most people do. So you're going to want to have a chart, a paper chart, wherever you're sailing. It is possible to do it mathematically, but very few people do that, so I'm not going to take time talking about it. When you're doing it graphically, there's a couple conventions that are good to follow. So let's suppose, so here we're leaving from Drake's Bay, which is right by Point Reyes, if any of you have been there. So let's say we've been sailing along for a while, and at 11:24 in the morning, our dead reckoning position tells us that this is where we think we are, okay? But we want to do better. We want to know where we really are, because we recognize there's all the errors. So what we're going to do is called triangulation. We're going to pick 3 things that we can hopefully see, and going to get our position from that. So I apologize if the magnification of the chart here is quite low, but right here, there is a mark that looks like an exclamation mark. Looks kind of like this. And so one thing that you should learn when you're learning sailing is you should learn how to read a chart. So if you've got a mark like that that looks like an exclamation mark, that is a lighted buoy. And so right here we have a lighted buoy because that's a shallow area right there. And big ships have to be careful because they could run aground. And so if we get out our compass and we take a compass bearing off of that buoy, let's suppose that the compass tells us that it's exactly 180 degrees. That's the bearing. So this thing is directly south of us. Okay, so what we can do is we can put a dot here and draw a line going down exactly south. And then if we follow that line back up again, then since we know that it's south of us, that means that we know that we're north of it. So we know that we're somewhere on this line. And so we look at our dead reckoning position, we say, oh, okay, well, good, that's what we thought. But we might actually be up here, we might be down here, we might be here. So we don't actually know that we really are there. We just know that we're somewhere on this line. So we need to do better. And the way to do better is we will cite something else. So let's say Point Reyes right there. And if it's nighttime, that's okay too, because there's a big lighthouse there on Point Reyes. So let's say that we take a compass bearing off of Point Reyes, and let's suppose that it's, say, 45 degrees. All right. So that means if we were to draw a line from here, from Point Reyes going off 45 degrees, if we backtrack that line, then this now becomes what we call a line of position, LOP, line of position. So we know that we're somewhere on that line, and from the bearing that we got of the light below us, okay. So where these two LOPs intersect, that would be our position. Now you don't want to go with just two sites because you know there's always going to be some error. And so what you want to do is you want to find a third thing that you can measure. So in this case, there's an island right here. It's called the North Farallon Island. And so what we'll do then is we'll take a bearing off of that. And let's suppose that that bearing works out to be, oh, no, let's say 133 degrees. So if we draw a line right there and then draw an arrow going off at 133 degrees, if we then back that arrow up, then what we have is a triangle. And hopefully it's a nice small triangle. And then we know that we are somewhere inside that triangle. Okay, so that way we have triangulated our position. We have fixed our position, right? So once you fix the position, then what you want to do is you want to mark that. And the convention that's used by pretty much all sailors is that if all you have is your dead reckoning position, you show that as being a half circle. But if you've actually fixed your position, then you show that as being a full circle with a dot in the middle. So that way, you know, you can have more confidence in it. So a half circle means that's only approximate, but don't bet your life on it. Whereas a full circle means, yeah, okay, then now we're pretty sure that that's where we are. So then as we continue on our sailing trip, this now becomes the starting point for our next portion of our dead reckoning position. So we head off here for a while, and then let's suppose that at 1308, okay, we want to fix our position again, but let's suppose that by this point we're so far out in the ocean that we can't see anything anymore. So we can't triangulate our position. So what we do is we bite the bullet and we get out the GPS. And so if the GPS tells us that at 1308, this is where we really are, then what we do is we show that as being a triangle. All right. And this is a convention that's used by pretty much all sailors. Half circles, full circles, and if it's an electronic fix, then it's a triangle, so that we know we can really have good confidence in that. But this technique here of triangulation is basically what we're going to do for celestial navigation, only we're going to be using stars instead of land masses. But it's a very, very similar approach. So let me pause there for a second and say, anybody have any questions about how to do land-based triangulation fixes? Give me thumbs up or thumbs down. Okay, all right, good. All right, okay, we'll go ahead and move on then.
I do have a question.
Uh-huh.
When you're taking those fixes with, say, binoculars, because it's further away, how do you take where the binoculars are and get a compass bearing?
Well, if you buy marine binoculars, there's a compass built in to the binoculars. So as you're looking through the binoculars, you will see a little compass inside the binoculars. So those are really nice.
I just need to get new binoculars. One more thing to buy.
Yeah, they're pretty expensive, but boy, they're nice. So if you don't have that, then you'll have to take a bearing off of something just without binoculars and just hold your compass up there and just do the best you can without the binoculars. Okay. All right, so here is the compass rose. And now in this enlarged version here, you can see a little bit more what's going on. So there's an outer circle, and then there's an inner circle. The outer circle is it's aligned so that it is pointing to true north. The inner circle, you can see in this case, has been tilted a little bit clockwise. So this is the one that points to magnetic north. And I trust that you guys understand that, magnetic north and true north are not the same. And depending on where you are in the world, they can be quite dramatically different. And so the compass rose will be adjusted properly for whatever region of the world this map is used for. And so all of the calculations that we are going to do as celestial navigators, we will always be referencing true north because that's all we have to work with. But when so when we figure out what direction we need to go, it's all going to be in true directions. And so what we'll need to do then is we'll need to convert that into magnetic when we tell the helmsman what course to steer. So let's suppose that we find that maybe 280 degrees is the direction that we want to steer, but that's true direction. So we're going to put a T after it. So then what we can do is we can look on the compass rose and read off of here. So if this is 280 here, we can just read off the compass rose what the magnetic heading is that corresponds to that. And so like in this case, it's about 15 degrees different. So then what we would have to do is we would have to subtract 15 degrees. And so we would tell the helmsman to steer a course of 265. Okay. And the compass rose just makes it a lot easier to do that. Okay, so I think we've talked enough about that. And this just shows you how the magnetic variation changes in the region of the world near the US. And it changes a lot. Okay, so this piece of paper that you see right here, this is what I emailed to you guys the other day. This is going to be an informal homework assignment that I don't expect you to do it right now, but at some point before we meet again, I think it'd be worthwhile doing this. For warm up here, just basically put in what is the number that corresponds to each of these. We know that north is 0 and east is 90, but what if you're somewhere in between there? What if you're exactly northeast? Okay, that would be 45, but what if you're something different? So this is a good little exercise just to make sure that you understand the compass and how to use that. And then this is a dead reckoning exercise. And so what we're going to do is we're going to assume that we're on a sailing trip, and we're assuming that we're leaving from directly under the Golden Gate Bridge. So this is the Golden Gate right here. So we're going to start off right there underneath the Golden Gate Bridge. And so leg 1 of the journey says that's where we start. And then part 2 says we sail on a heading of 247 true. And these are all true. I didn't want to confuse things too much. So all the numbers you see up here are true. Okay, so we go off on a heading of 247 true for a while. And so this is where you're going to use the protractor to figure that out. And then you're going to go for 11 nautical, or however many nautical miles that is, let's see, let me get my glasses on. Okay, yeah, it's 11 nautical miles. Okay, so now the question becomes, how do you know on this map how far is 11 nautical miles? You guys are probably used to land-based maps where they all, down at the bottom of a land-based map, they always have a scale. And so you can get out your compass, which, by the way, I recommend everybody get one of those. Okay, so you get out your compass and you put it down on the scale at the bottom of the chart and put it so it corresponds to 1 mile. Okay, but nautical charts don't have a scale on the bottom. Any of you guys know how to figure out the scale on a nautical chart?
Is it 60 miles between degrees?
Very good.
So you
Yes.
just have to figure it out by eyeballing it?
Well, you don't have to eyeball it. If you look over on the right and left sides of the chart, you'll see they've got the latitude scale right here.
Ah, I see
On
this.
both
Those are
sides.
10-mile things.
Yeah. So if you just look off here, then you can find out what the scale is. So this right here is 37 degree. Oh, it's 36 degrees right here. And this is 37 degrees here, and this 38 degrees here. So from here to here is 60 nautical miles. And if you want to do better, if you look at the different divisions here, so there's 10, 20, 30, 40, 50, 60. So from here to here, that would be 10 nautical miles. Okay, so what you can do then is you just need to get out your compass here, the drawing compass, not the direction compass, and then go over to either the right side or the left side, and then set it off for 11. So it's 11 nautical miles, or 11 minutes of latitude, and then just put that on the chart, and then that'll be 11 nautical miles. Okay. Now, when you're using the nautical chart here, make sure that you use the latitude scale and not the longitude scale. Okay, because, whoops, sorry, I gotta remember to turn on annotation before I touch my screen here. So 60 degrees equals, or I'm sorry, 1 degree. Let me try that again. So 1 degree of latitude equals 60 nautical miles, but that's not true for longitude unless you're at the equator. If you are at the equator, then 1 degree of longitude would equal 60 nautical miles. But if you're anywhere north or south of the equator, then that's not going to work. But the latitude scale will always work no matter how far north or south of the equator you are. So just measure off 11 nautical miles, and then come here, and then put a half circle right there. And then the next part of it says, okay, then we head down here for a while, and then we turn over here for a while. And so when you finish, if you do everything right, you should finish up somewhere here in Monterey Bay, and you should be really close to the shoreline, close enough to where you could drop anchor and spend the night. Okay. And so this is a really good exercise in dead reckoning. And so sometime between now and the next time we meet, I'd like you guys all to do it. Now, if you don't like spoilers, then close your eyes for just a minute. But if you do like spoilers, okay, this is where you should end up. Okay, so in Monterey Bay, there's another one of these symbols here that looks like an exclamation mark, except it's off on its side. Okay, so this mark that you see right there, that's a light that's intended for navigational purposes. So it can be seen even if you're out quite a long distance out into sea. So if you do everything right, you should end up right next to this nautical light in about halfway down Monterey Bay.
What was the mark that was straight up and down?
The exclamation mark? Is that what you mean? Yeah. When you
Yes.
when you look on the charts here, you'll see that the exclamation marks are quite often not straight up and down. You know, quite often they'll be off on a side like this. In fact, I mean, here's one that's actually upside down, and here's one that is off on the side. Here's another one that's upside down. So it just the the dot tells you where the light is located, and then this little teardrop type shape that just alerts you to the fact that it is a light. Okay. So when you do the homework assignment, if you do it right, you should end up right there. Okay. So now let's talk about how a celestial navigation activity is similar and how it's different. Okay, so the key, well, the first thing we're going to do is we want to measure what we're going to call the altitude of the star. And so whenever you hear me say the word altitude, I don't mean how many feet above sea level it is. What I mean is what is the angle above the horizon. So this dark blue background that is the background for all of my slides is actually, it's a photograph of the ocean. And here, let me turn on annotation. Let me switch to a different color that hopefully will show up a little better. Okay, so this line that you see right here, that is the horizon. And all down below is just water, and up above it is sky. Okay, so what we are going to want to do is we're going to want to measure the altitude of a star. So what that means is we just want to know how many degrees is it above the horizon. And so what I mean by that is, if I were to point one arm at the horizon, point the other arm at the star, what is the angle in between? That is the altitude. So you're going to hear me using that word an awful lot here. So there's a bunch of different ways that you can measure altitude. One way is what you're seeing right here is called a mariner's quadrant, which is very, very similar to what we're going to be using for tonight's homework. What we're going to be doing for tonight's homework is we're going to take a simple protractor, we're going to hang a weighted string from it, and then we got the markings here, so we're going to read off of here what the altitude is. So mariners used to use this for many, many years. It just works exactly the same way. So it's really simple, easy to understand. This is what we're going to be using tonight. We do have to be a little bit careful because the protractor that we're using is not actually intended for this particular application. And so the number that we read is going to be a little wrong. If we were measuring something that was exactly on the horizon, so our protractor would be pointed like this. And so when it hangs down here, it would be reading at 90. Okay, so what the protractor calls 90 is what we are going to call 0. And so when you guys do tonight's homework, what you're going to need to do is you're going to need to correct for it. So like, let's suppose that tonight when you measure some stars, your protractor ends up looking like this. So you can see that this is, let's see, this is 90, 80, 70. So the protractor is going to read 60 degrees. But that's not really what the altitude is, because remember, 90 degrees is really 0 for what we care about. So 80 degrees would really be 10, 70 degrees would really be 20. So when the protractor reads 60 degrees, for us, for our purposes, that's really 30. So when you do the homework tonight, take the difference between what the protractor says and 90, and that's going to be the altitude that we're going to want to use for tonight's homework. Okay. All right, now the real way to do it is with the sextant. But if we were to talk about how to use a sextant tonight, we wouldn't have enough time to do the other stuff, which I think is more important to do first. The sextant can wait until next time. My goal for you guys tonight is for you to be able to measure stars, put the numbers into your smartphone, and get a number out. And so we're going to have to skip sextants, but we'll spend the whole time next time talking about that. But just in case you hadn't yet purchased your sextants, here are the ones that are available. And I guess you guys have already seen this. You've already been to Celeste Air's website. So this is the one that I use. There is one that they call the professional version that is made out of a type of metal that is slightly more temperature stable. But this Astra 3B is great. I mean, I think the Astra 3B is every bit as good as either the Cassinson Plate or the Tamiya that cost twice as much. I have used my Astra 3B for 30 years and absolutely loved it. Now you guys are going to be using the Davis Mark III. This one is about as cheap as you can get, but it gives really good results. I think you guys will be happy. If all you're ever going to do is emergency navigation, you'll be happy with that. But if you're willing to spend the bucks, I would recommend you get the Astra 3B rather than the ones that cost twice as much and aren't really any better. Okay, now, when you measure things with a sextant, you may have heard that there's a bunch of corrections that you need to worry about. For what we're going to do tonight, you don't need to worry about any of these, but I just want to talk about them briefly because I know that some of you have probably heard about them and you want to know what they are. So one thing that you have to worry about when you're using a sextant is the fact that the angle that you measure is not going to be completely correct unless you're actually swimming in the water. If your eye is even a little bit above the water, the horizon that you see is not really the true horizon. And you can see that even if you're only 4 feet above the water, the fact that what you see is not really the true horizon is enough that if you didn't take that into account, when you do the final numbers, your position would be off by almost 2 nautical miles. And then the higher you are above the water, the worse this error becomes. And so we are going to learn how to correct for this, but not tonight, because the method that we're using, we're not using a sextant, we're using the protractor. And so eye height, it doesn't even come into play. But if we were using a sextant, we still wouldn't have to worry about it as long as we use the smartphone to do the math for us. Because what the smartphone is going to do is it's going to ask us what was our eye height when we made the measurement, and we will just tell the smartphone what it was, and then the smartphone will automatically make these corrections for us. So we don't need to worry about it even when we do use a sextant. Same thing with refraction. You may have heard that when you look at some object in the sky, be it the sun or the star or whatever, you think that the object is right here because that's what it looks like. But in fact, it's actually lower in the sky than it really is because of refraction. Okay, so when the light rays come in from the sun or the star or whatever, when they hit the atmosphere, they get bent. And so the sun or star that we're looking at is not actually located where it appears to be. And so then we have to do what's called refraction correction. And you can see here, if the lower the thing is on the horizon, the bigger this problem becomes. And so correcting for it is very important if you're using a sextant. And in fact, even if you're using the protractor, it needs to be corrected for as well. But the numbers we're going to get with the protractor are so rough that this is the least of our worries here. But when you're doing with the sextant, again, as long as you're using the smartphone app, the smartphone will make these corrections for you, so you don't need to worry about it. When you measure the sun, what we're going to find is that you can't really measure to the center of the sun the way that you'd like to. So what you do instead is you measure to the bottom edge of the sun or the upper edge. And then you have to correct for that. But again, as long as you're using the smartphone will take care of that for you. So all these things, and parallax is another thing that we'll talk about later. I don't want to spend too much time on this. We're going to talk more about this later. But the important thing is all of these errors that you may have heard about, you don't need to worry about for tonight. And in fact, even next time we meet, as long as we're using the smartphone, it's going to take care of all these things for us. So, so it's makes things a lot simpler. Okay, so we are now going to jump into how celestial navigation works. We're going to talk about the theory of how celestial navigation works. And I propose to you that the theory is actually really easy. It's way easier than people have feared. The difficulty is there's so many little corrections, like the corrections we've been talking about for the last 2 or 3 minutes. Making those corrections is quite tedious, and that is what makes celestial navigation difficult. The fundamental theory of how celestial navigation works is, I think you will agree, is actually very, very simple. So here's what we're going to do. Okay, we are going to measure some star. We're going to measure the altitude of some star. And so I'm going to throw in a whole bunch of vocabulary here. Let me draw some pictures. So if we are located right here, if we were to point one arm at the horizon, this right here is where that would be. This is the horizon line. Okay, and we're going to point our other arm at the star. And so this is the other arm going at the star. So the angle in between here, this is the altitude. This is what we are going to measure. But it's not actually what we really care about. The thing that we really care about is this other angle over here, the one that's called the zenith angle. So this is called the zenith angle. Okay. And the way you would get the zenith angle is you would point one arm directly above your head. Okay. So if it were possible to somehow point perfectly straight upwards and be absolutely certain that you're perfectly straight upwards. And then if you were to bring the other arm down from that point to the star, that angle there is called the zenith angle. And that's the angle that we really care about. The problem is measuring this angle with high accuracy is very difficult because you don't know when you hold your arm straight up, you don't know that you're holding it perfectly up, and you might be off a little bit, right? So measuring the zenith angle turns out to be extremely difficult. And so, but measuring the altitude of the star, you can do that very easily. If you have a section, you can do it with really high precision. So what we're going to do is we're going to measure the altitude, and then we're going to take 90 minus that altitude in order to get the zenith angle. And that is what we're actually going to be working with. Now, the reason why the zenith angle is the important one is because if you look at the zenith angle and you look at this other angle right here, okay, they are the same. In mathematics, you probably remember if you got two parallel lines cut by a transversal, you know, these angles right here, they're called alternate interior angles, and you know that they're the same. So if you can figure out what the zenith angle is for the star, then that tells you how far you are away from this point right here. And so I'm going to introduce a new term here. I'm going to call this the geographic position of the star. Okay, geographic position is usually just abbreviated GP. So you're going to see GP written a lot here. So the geographic position of the star is if you had a friend. Okay, so let's say that you're sailing and you're over here, and you've got a buddy who is sailing, and by sheer coincidence, your buddy just happens to be located at this point right here, where if your buddy were to point his arm at the star, your buddy would be pointing directly above his head. Okay, just by lucky coincidence, your buddy just happens to be located directly on the line in between the center of the earth and the star. Okay, so this position right here is called the geographic position of the star. Okay. And so if you measure the zenith angle, what you've measured is how many degrees you are away from the geographic position of that star. So let me pause for just a second. So far, so good. Give me thumbs, either thumbs up or thumbs down. And you don't have to turn on your camera to do that. You know, down at the bottom there, you've got these reactions here. So you can do thumbs up by that way too, if you want. Okay, so we're all good that, so our zenith angle is equal to how far we are away from the geographic position of the star. Well, it turns out that the geographic position of the star is something that you can look up in a book. It is very easily known. This book that you see right here, this is called a Nautical Almanac, and they print a new one every year. So this was a really old one here. So this is a book full of tables, and so let's suppose that I have measured the altitude of some star. Let's say I've measured Arcturus, right? So I know how far I am away from the geographic position of Arcturus, but I need to know where is the geographic position of Arcturus. So if I look in this book here, they've got all these tables, and I can look it up here, and it will tell me for any time on any day of this year, it'll tell me what the geographic position of Arcturus was at that time. And now your smartphone has that same thing built into it. The smartphone app that you guys downloaded, it has all of this information built right into it. Okay, so using either the Nautical Almanac or the smartphone, we can find out what was the geographic position of the star at the instant that we measured it. And then if we know what the zenith angle is, then that tells us how far we are away from the geographic position. And so what we can do then is we can say, okay, we now have a line of position. We now know that we are somewhere on this line. We might be here, we might be here, we might be here. We don't know where on the line we are, but we know we're on the line. This is exactly the same as we did back when we were doing terrestrial-based navigation a few minutes ago when we were doing that sailing exercise off the coast of San Francisco. What we did was we took a bearing off of one object and we got a line of position from that. And we took a bearing off another object and we got a line of position from that. Well, that's exactly the same as what we're doing here. Only in this case, instead of being a line of position, it's a circle of position. So we know that we are somewhere on this circle. Well, we'd like to do a little better than that. We'd like to know more precisely than just somewhere on that circle. So anybody have any suggestion what we could do to get our position better than just that?
Use
Turn on GPS.
Can't argue with that.
take a sighting of the sun to find out at its zenith what our latitude is.
We could do that. So basically look at another object is what you're saying. Yeah. So what we do is we look at another object. It could be the sun, could be another star, it doesn't matter. So we're going to repeat the process again with a different star. And so we get a new line of position, which is actually a circle of position. Okay. And so wherever these two circles of position cross, that is our position. Okay. Now you want to do it for the best accuracy, you want to use more than just 2 stars. You'd actually want to use 3 stars. But just to keep the drawing simple here, I've done it with only 2. So what we've got here is 2 circles, and wherever these circles overlap, then bingo, that's where we are. Now, every year I always have somebody say, well, hey, Doug, when circles overlap, they overlap in 2 places, not just 1 place. So how do you know whether you're at this interlap or whether you're at this interlap or this overlap? Well, one of these points of overlap is going to be in the Atlantic Ocean, and the other point of overlap is going to be like in the Indian Ocean, or maybe in, in Asia or something like that. You shouldn't have too much trouble figuring out which one you are. Okay. All right. So that is the heart of celestial navigation. Now, the details are very tricky. Okay. But the fundamental theory of how it works, I think, is really, really, really simple. And give me thumbs up if you agree, or give me this if you disagree. Okay. So, all right. So, okay, good. Yeah. So the fundamental theory is really easy, but boy, are there ever a lot of details that make it a little bit tricky. Okay. All right. So, okay. We, for tonight, and then also when we meet next week, we are going to let the smartphone do all of the mathematics, all of the calculations for us. When we meet on the third class session and the fourth class session, that's when we're going to put the smartphone away and do the math ourselves. But everything we're going to do in tonight's homework and everything that we're going to do in a week from now, we're going to let the smartphone do all the thinking for us. So now we move into the second big item on my agenda for today, is we're going to learn how to use the smartphone. Because remember, my goal is that when we're done 1 hour from now, I want you guys to be able to go outside and measure 3 different stars and get the numbers from here. And then you're going to take those numbers, and you're going to put them into the smartphone, and then the smartphone is going to tell you where you are. So let's see how this works. Okay. Let me skip over that. Okay. Now, there is one rather important detail, is that before we can put the numbers into the smartphone, we need to be able to tell the smartphone which star we measured. If we don't know that, then we're hosed from the get-go. Okay, so before we learn how the smartphone works, let's take a minute or take a few minutes, and let's learn how to identify stars. Okay, so now some of you have smartphones that if you hold it up to the night sky, the smartphone will tell you what star it is. That's cheating. And by the way, a lot of them get it wrong too. So I wouldn't trust that too much. So the other day I emailed you guys this file and I asked you to print it out. Do you guys all have that with you? Okay. Everybody, you got it? Okay, good. All right, so we're going to learn how to use this chart, because this is what you're going to be using tonight when you go outside and identify some stars that you're going to measure. Okay, so the first thing that you should do is I'd like you to hold it so that the writing is normal. And if you look down at the bottom, you'll see the word south written down here. Okay, so when you walk outside tonight, what I want you to do is I want you to face south, hold this thing in front of you, and then I want you to cover up the top half of the circle. You're only going to look at the bottom half of the circle. And so what you see in the bottom half of the circle should correspond to what you will see in the night sky. Now, there's not a whole lot of really interesting things in the south part of the sky there. So tell you what, rather than pointing south, let's rotate this a little bit so that you see down at the bottom where it says SW. Okay, you see right there it says SW. So what I want you to do is I want you to rotate the page like this so that SW is at the bottom of the circle. And so then what I want you to do when you go outside is I want you to face southwest rather than south. Okay. But again, I want you to cover up the top half of the circle. Okay. And now this time, if you do this quite soon after class ends, you should see a very bright star very low on the horizon. And that bright star that you're going to see, it's not going to be exactly southwest. It's going to be a little bit to the right of southwest. But that bright star that you see there is Sirius. And you guys should be able to see that with no trouble at all, because Sirius is actually the brightest out of all the stars in the night sky. Sirius is the brightest one. So even if you're in a metropolitan area that has a lot of light pollution, you'll be able to see Sirius. But make sure you do it very soon after class lets out, because if you wait too long, then it's gonna set beneath the horizon. But the closer the star is to the outer edge of the circle, that means the lower it is in the night sky. So if you can locate Sirius, then if you look directly up above that, you'll see there's another dot that's a little bit larger than the other dots. And that dot is labeled as Procyon. Okay, so that's going to be up a little bit higher in the night sky. And in fact, the closer you are to the center of the circle, the closer you are to being directly above your head. So this cross that you see in the center of the circle there, that is what we call the zenith point. That's the point that's directly above your head. Okay, so if you're looking to the southwest, you should see Sirius and Procyon. Okay, now what if you look directly west? Well, take the sheet here and rotate it completely like this, 90 degrees. So now if you look down at the bottom, you'll see it says west down at the bottom. Okay, so then what you need to do is face west. And if you do that, then you'll see the quite bright star there that's Betelgeuse. It'll be a little bit higher above the horizon than Sirius was, but not much. It'll still be pretty low on the horizon. And then you go directly up above that, you'll see one called Pollux. And so that's how it works. So depending on which way you've got this circle oriented here, okay. Now remember, you're always going to want to cover up the top half of the circle, because anything that's in the top half of the circle is going to be behind you. The lower half of the circle, those are going to be the stars that will be in front of you. Top half of the circle, those are the stars that are going to be behind you. Okay. Everybody good on how to use the star chart? Can you give me thumbs if you are? Okay, good. All right. Okay. Now, the star chart contains a lot more stars than we really care about. Celestial navigators, a long time ago, they went through the night sky and they did a study of all the stars in the night sky, and they picked out 57 stars that they selected as what are called the navigation stars. And these 57 stars were chosen on the basis of two criteria. One is that it has to be one that's really bright. And then the other one is that they were spaced out so that no matter where you are on the earth on any night of any month, okay, there will always be at least a half dozen of the navigation stars somewhere in the sky above you, no matter where you are, no matter when you are. Okay, there will always be stars there. So these 57 stars, these are the ones that your smartphone knows. And these are the ones that are listed in the Nautical Almanac. And so those are the only ones that we care about. So how do you know which stars are the navigation stars? Well, if you look in the workbook that I sent you, you'll see on page 10, there's a chart that looks like this. This is a map of the sky that doesn't completely represent how the sky really looks, but it shows the whole sky. I mean, you guys know that when you look at a map of the world, anything that's very far north or south of the equator, it's all stretched out, like Greenland. Greenland looks huge on a map of the world. But if you look on a globe of the world, you'll see that Greenland isn't really that big, right? Because what they did was they took the globe and they stretched it in order to put it on a flat piece of paper. Well, this chart right here suffers from the same problem. What they did was they took the night sky and they stretched it in order to get it to fit on a flat piece of paper. So anything right around here is pretty close to what it will look like in the real night sky, because this right here is the celestial equator right here. So anything that's close to the celestial equator, if you look up in the night sky, that's what you'll see. But if you get up very far above the equator, then you're going to see that things are kind of stretched out, so that it will be a little confusing at first. But the important thing is that it's got all of the stars on it that are important. So what you see here, these stars, these are the navigational stars. These are the 57 stars that you need to know. Okay, so what I would recommend is, let's take the chart that you guys are going to be using tonight, and I will tell you, just to make your life a little bit easier here, I will tell you which of these are the navigational stars. So so get out a piece of paper, or get out a pen and get out your map. And so let's start off. Well, let's start off with Sirius, because we've already talked about Sirius. Okay, so Sirius is one of the navigational stars. Procyon is. Betelgeuse, Capella, Pollux, Aldebaran, often pronounced Aldebaran, but yeah, I don't guarantee that my pronunciation on all these is 100% correct. Okay, Spica is a good one to know. Arcturus, those you're going to want to know. Vega is a really good one to know. The ones, the brightest stars, you know, Sirius is number one. It's the brightest out of all of them. Vega is good and bright. Arcturus is nice and bright. Spica is nice and bright. Capella is nice and bright. So when you do the homework tonight, those are the stars that I would recommend that you measure. But if you want, you could also do these others. Pollux, those are good. Let's see, what's another one here? This star right here, the one that's the cup of the Big Dipper, that one is not named on this chart, but it's actually one of the navigational stars. That one is called Dubhe. And there's a couple more that I could go with, but tell you what, let's not spend all day doing this. If you can identify these stars, then you can measure their altitude using the protractor. And when you go to put the numbers into your smartphone will recognize these stars. But if you were to pick some of the other stars on the list here, your smartphone is going to say, hey, I don't know that star. That's not one of the navigation stars. I can't do anything with that. Okay. So I need some sort of feedback. Again, I'm sorry if you guys think that I'm needy, but I do teach. I teach high school. And one of the things that I learned early on was always get feedback. Okay, so I'm seeing some thumbs up. Okay, good. All right. If you guys think I'm going too fast, let me know. If you think I'm going too slow, let me know. But otherwise, I'm going to just plow forward. Okay, so when you go outside tonight, in about an hour from now, your job then is to find those stars, and then take a protractor like the one that you see here, and put some sort of a weight on it. Okay, and then just look through this. You don't have to put a straw on the end if you don't want, but it makes it a little easier to do it. So look through the straw until you're looking at one of those stars we've just identified, and then come down here and see what the angle is on the protractor. And then remember that the number that's shown on the protractor is not the number that we want. We have to subtract it from 90, because for us, 0 degrees on the horizon corresponds to 90. So what we're going to do is we're going to measure at least 3 stars. Now, you can measure more. And in fact, I recommend that you do measure more. Your smartphone can accept, 5, 6, 7, 8. You can do as many stars as you want. The more stars you do, the higher your accuracy is going to be, because if you have any errors, they get averaged out, by doing lots of measurements. The errors become less significant. Okay, so now that we know how to measure, how to identify the stars, and we go out and we've measured the stars. And by the way, for the planets, you need to have a chart that is current for whatever day you're interested in, because the planets move around. So they're a little bit trickier to find. But your smartphone can give you a map that will be current for whatever day you're interested in. And so you see this circle on the smartphone. So this is the Android. This is what the Android app looks like. And over here, this is what the Apple app looks like. And it will give you a circle that works exactly the same way as this guy does. Okay, so if you want to use this, what you do is just, remember, always use the lower half, because the upper half are going to be stars that are behind you. And so you can get them this way. So let's see now, let's suppose now that we've measured a bunch of stars, we've identified them, measured them. Now it's time to put the numbers in there. Okay, so what we're going to do is we're going to reduce the numbers. Okay, so for what we're going to do over the next couple minutes, we are going to use numbers that are in the workbook that I gave you. On page 18, I give you some numbers here that that we are going to put into the smartphone exactly the same way that you're going to put your numbers in tonight. So on problem number 18 on page 14, sorry, I think I said page 18. It says problem 18 on page 14. So we're going to assume that we're sailing and we're somewhere near this position. What you see right here, this is our dead reckoning position. Okay, we know that it's wrong, but we also know that it's at least close. So this is where we think we are. And what we're going to do here is we're going to pretend that we have measured 3 different celestial objects. We measured the planet Jupiter, we measured the star Rigel Kentaurus, and then we measured the moon. And so these are the times that we measured them. And then this is the date that we measured it. And so all we need to do now is we need to know how to put them in the smartphone so the smartphone can tell us what our position is. Okay, so let's learn how to use the smartphone. All right, so by the way, I forgot to ask this when I was taking the survey. How many of you have the Android app? Raise your hand if you got the Android app. How many of you have the iPhone app? Okay. Oh, wow. And Alex, I didn't see you. What were you at? You Apple or Android?
I'm Apple, but I was trying to resurrect an Android phone because that app looked really nice.
Yeah, I
So-
like the Android app better for sure.
Yeah, the Apple one's expensive.
It shouldn't
Yeah.
be. It shouldn't. It
It
should
was-
only about
It was
$20.
like $20.
Yeah. Okay.
The
yeah.
Apple one doesn't know your position. Is there a reason you can't just push a button and it figures out where you are for?
They could easily have done that, but the programmers just didn't bother to. But yeah, okay. So it looks like most of you guys are Apple users. Okay, so that's good to know. All right. So what I need you to do is fire up your app. And those of you on the Apple, you're going to open up the Celestial app, and you should see a screen that looks like you see on the left side. Those of you that are Android app users, you're going to fire up the app that's called Astro Calculator, and what you will see is on the right side. Okay. So give me thumbs when you've got the app up and running. Okay, good. All right. Okay. So if you're an Apple user, then the first thing you want to do is you want to select trips. If you're an Android user, then if you were doing it for real, what you would do is you would do position fix calculator. But for what we're going to do right now, we're going to use what are called the education tools. So we're going to use the site reduction calculator. It does the same thing that the fix does, but it shows us some intermediate results that will help us to understand more about what's going on. So if you're an Android user, site reduction calculator, and if you're an Apple user, do trips. Okay, so when you do that, it should take you to a screen that looks like this. And so what you're going to want to do on iPhone is you're going to want to add a new trip. And if you are on the Android, what you're going to want to do is you want to tell it intercept method is what you want. Okay. Next, those of you that are Apple users, you need to add a new site group. So what's happening here is that the people who wrote the iPhone app, they organized everything into kind of like folders is a good way to think of it. So if you're on, let's say you're sailing to Hawaii. So all of the sites that you are going to be calculating on the entire journey will be put into this folder here. The default name for the folder is trip 1. By the way, you can change that name if you want, but for right now, let's not worry about it. That's just the default name. And then each time that you go out in the evening to take sites, then that is going to be a separate site group. So within one trip, you're going to have dozens of different site groups. And then each site group will be all of the measurements that you took at one sitting. On the Android, they don't do it this way. They do it differently. Okay, so now that we've gotten this far, now the default name for by the way, is group 1. You can change the default if you want, but for right now, let's not waste time with that. Let's just go with the default name. Okay, so we are ready now to take our first site. So that means we're going to measure whatever object is we happen to be looking at. Okay, so first thing we need to do is we need to tell the app what body we measured. Okay, so if you're an Apple user, what you're going to do is you're going to push right here, and it's going to give you a drop-down list that you can scroll through. And if you're an Android user, what you're going to do is the same thing. You'll push, you'll select this thing right here, and it'll give you a list to scroll through. So what I want you guys to do is scroll through that list and find Jupiter. And then once you've got Jupiter, what I want you to do is give me thumbs up so that I'll see that you got it. And it actually works best if you use the reactions button rather than giving you a real thumb. It's easier for me to see that way. So I'm seeing one thumb up, but that's the only one. Okay, now I'm seeing lots of thumbs up. Okay, good. All right, so let's move on to the next one. Okay, so we've told it what it is we've measured. Next thing we need to do is we need to tell it the day and the time. Now, when you look in the workbook, it's going to tell you that the local time and the local date were, well, let's start with the local date. Okay, in the workbook, it says that it's the evening of May 10th, 2005 locally, okay? Emphasis on the word locally. Everything that we put into the phone here, it has to be Greenwich time and Greenwich day. So if you read through the problem, you'll see it tells you that even though it's May 10th where you are, back in Greenwich, it has already passed midnight. And so Greenwich, it's actually May 11th. Okay, so what you need to do here is you need to tell it 2005, May 11th. Okay, and then you need to tell it what time it was when you measured Jupiter. So if you look down further down on the page here, you'll see it says that when we measured Jupiter, the local time was 1742. But again, the time that we care about is Greenwich Mean Time. universal time. So in parentheses, you can see it says that in Greenwich, it was 1:42:18. So it was 1 o'clock in the morning, almost 2. So 1:42:18, that is the number that we need to put in there. Now be careful you don't get the day and the month mixed up. On the Android app, when you're putting it in here, that's the day first and then the month second. Other apps do it the other way around. So be careful you don't get those mixed up. That's an easy mistake to make. Okay, so everybody give me thumbs when you got that. Okay, Alex and Paul, you got it? Okay. All right, good. Okay, so we got that in. All right, next step is we need to tell it what our assumed position is. This is the number that we're going to get from our dead reckoning. The number that we know is not correct, but that's okay. As long as it's within 100 or 200 miles, that's good enough. That'll work. Okay, so according to the problem statement in the workbook here, it says that our assumed position is 22 degrees, 57 minutes south and 118 degrees, 16 minutes west.
How do we put that in with the degree sign and stuff?
No, you don't put a degree sign. Just put 22. Let's see, boy, rats. Where did I put my? Yeah, I don't have an iPhone. So, and I did use one several times while I was preparing this. I think it's 22 space 57. Did that work for you? 22 space 57?
Yeah,
Yeah, I
that
did a
works.
space, but you just have to proceed it with the S.
Okay. Yeah, I think next time when we do this next week, I'm going to get hold of an iPhone and I'll get
Yeah, that
some
works.
better screens. Okay, that worked for you? Okay, so give me a thumbs up once you've got the position entered in. Okay, Alex, you getting it? You've got a concerned look on your face there, Alex. Is there a question you can ask that will clear things up for you?
No, I'm just reading and exploring.
Okay, all right.
That's
Okay,
my
so
focused face.
Okay, all right, so let's move on then. So we've entered our assumed position. Now, the next thing is it's going to ask us if we are experiencing any unusual temperature and pressure situations. If the pressure is super low, that will affect things slightly, but really only slightly. And the only time the pressure is going to be that low is if you're in the middle of a hurricane. So if you're in the middle of a hurricane, you're not going to be able to do any site measurements anyway. And also, if you were up at the North Pole or down at the South Pole, where the temperature is really, really cold, that affects things too. But that's not going to affect us. So we're just going to ignore that. You can just go right by that. You don't need to enter anything in for that. Okay, so the next thing you need to do is you need to tell the smartphone what was your index error and your eye height. Now, index error is anything if your sextant is misadjusted. So we're going to talk about sextants in gruesome detail next time we meet. But some people, if their mirrors are a little bit misadjusted, rather than correcting the problem on the mirror, some people are afraid to touch the mirror. They're afraid they're going to break it. So what they do is they just note that their sextant has a certain amount of error. And then they just live with that error. And that error is called index error. So for tonight's assignment, we're going to assume that we have correctly calibrated our sextant. So we do not have any index error, but we are assuming that our eye is 5 feet above the ground. So we need to tell it that our eye height is 5 feet. Now with the iPhone app, the default might be meters, not feet. So when you put in 5 and then you back, oh, another thing about the iPhone app that I think you guys have already figured out that's kind of annoying. When you go in to put the numbers there, it doesn't give you a next button. You have to back up to get back to this screen, which is a little bit awkward. But so put in 5 and then back up. And does it say 5 feet or does it say 5 meters?
It says
Neither.
5 feet, but I have the settings set for feet instead of
Okay,
metric.
all right. So if it tells you 5 meters, then go in and change your settings there because we want to be working in feet. Okay. Give me thumbs if you're ready to move on to the next step.
Mine doesn't say 5 feet. I put in 5 and it doesn't have anything there.
Okay, now back, hit the back button. This is the thing about the iPhone app that I remember was really troubling. After you put in the 5, you have to back out to the previous screen, and then you should see, it should tell you then whether it's 5 feet or 5 meters.
It doesn't. It doesn't on my phone. I just put in, I go to a sextant corrections and then put in HOE, height of eye 5. And I hit back on site and it doesn't say anything there.
Are you on the iPhone or are you the Android?
iPhone.
Oh. The rest of you guys did it, right?
I got the same 5. It didn't say feet.
Mine's saying feet. What if you went into your settings and picked between the two? Do you need to do that?
I did that and then I came back, I lost the entire site. So I have to put it all in again.
Oh,
Yeah, I don't want to do that.
But it was already set to feet.
Okay.
I haven't changed anything.
Okay, well, we'll tell you what, guys, I'm worried that we're going to run out of time.
Okay.
So if you haven't quite got it, let's just proceed through as if you did. And this is all being recorded. And then
Oh, I got it now.
Oh, you got it. So what did
Yeah, you have to put in, you have to actually put in 0 for your, if you don't put in 0 on your,
on the correction?
the
index
correction,
error?
you don't, yeah, so that was
Oh.
the issue. Sorry.
Okay, all right. Okay, good.
I have it now. Feet.
Okay, good. Yeah, I definitely like the Android app much better than the iPhone app. Okay, so let's move on to the next one now. Okay, so now we're going to tell it what the section reading was. Okay, so if you look in the workbook, it says that when we measured Jupiter, we found that the section reading was 33 degrees and 48.9 minutes. So everybody please put that in. And then give me thumbs once you got that in. Okay, good. Okay, excellent. All right, so now here's where the fun begins. This is where the important stuff. So what we're going to do now is we're going to calculate intercept. So please go ahead and do that. And when you do that, it should show you a screen that looks like this, and hopefully you got the same numbers that I have. Okay.
Nope. So I'll go back and see if I did.
Well, what I would recommend is if you don't have
Actually,
this,
all the numbers are the same except for distance.
okay. What do you have for distance?
23.0 away.
I have 40.5 away.
I have 40.5.
Okay. All right. All right. So so what I would recommend is that if you don't have 40.5, then pretend that you do, because otherwise we're going to run out of time here. Okay. So let's talk about what these numbers mean. So remember that what we're doing is we're measuring a star, and we want to know how far we are away from the star's geographic position. And once we know that, then we can draw a circle on the globe, where that circle is a circle of position, but we're going to call it a line of position. And so what we just found out is that line of position is 40.5 meters further away than our assumed position. And by the way, I'm interested that you guys are saying that you're getting 40.5 rather than 50.5. Okay, what that tells me is that I think the Celestial app may have changed their algorithm a little bit since I did it here. It used to be that if you measured a planet like Jupiter or Mars or something, the number that you got using the Celestial app and the number that you got using the Android app were sometimes as much as 10 miles different. And the reason for that was because the motion of planets is difficult to predict with super high precision. It's much more difficult than it is with a star. You guys know what retrograde motion is? You know that if you were to take a map of the stars, in fact, tell you what, I think I got a minute here. So let me open up a whiteboard. If you were to look at a map of the stars and you say, okay, here's one, here's one, here's one, here's one, here's one. And then on this map, you would say, okay, where is Mars? So then you'd say, okay, well, Mars is right here. Okay, well, great. But wait a week and do it again. And then you'll find that Mars is not there anymore. Mars has now moved. Now it's over here. And a week later, it's over here. And a week later, it's over here, and so forth and so on. Mars moves through the sky at a different speed than the stars do. But what's really interesting is that Mars will move this direction for a while, and then it'll slow down, and then it'll start going backwards over the course of several weeks, right? It's moving backwards, and then it'll turn around, and then it'll start going forward again. So during this time when Mars is moving backwards, we call that retrograde motion. And because of the fact that planets undergo retrograde motion, then if you want to predict where that planet's going to be at any time on any day, you have to use some really high-powered, sophisticated mathematics. And the smartphone is an amazing device, but it's not super accurate when it comes to the planets. I mean, it's amazing that it's as good as it is, but it's not perfect. Whereas when it predicts the geographic position of the stars, it can do that with high precision very easily. But the planets are a little bit harder to do. Okay, so it used to be that the iPhone and the Android had slightly different results when you were calculating planets. But if you calculated stars, then they always agreed really well. But planets, they were sometimes a little bit off. But the fact that you guys are now getting a different answer on your iPhone, now you tell me you're getting 40.5 rather than 50.5. So that tells me that the celestial people must have improved their algorithms compared to what they used to have. Okay, so anyway, we now know that the line of position is 40.5 miles away from where we thought that we were. And now if you look down here, you'll see it says
somebody's
ZN.
volume is turned on. I can't hear you very well.
Here, I'll just mute everybody. Okay, so I have the ability to mute everybody here.
Can you go for that distance away thing one more time? What it means?
Yeah, that's what I'm going to do right now. In fact, I have some slides that I think will make it very clear. In fact, let me just jump right straight to the slide. Okay, so here I think will help you. So let's pretend that our estimated position was right here as shown on the chart. Now the numbers that we put into problem number 18 are actually nowhere near San Francisco. But just for the sake of illustration, let's pretend that this black dot that you see right here, Okay, let's pretend that that's our estimated position. Okay, so the smartphone is telling us that the line of position, which is really a circle of position, is 40 miles further away from our position than where we thought we were. And the smartphone is also telling us that if we wanted to point our arm at the star, then we would have to point it at an angle of 77 degrees. Okay, so let's see what that corresponds to on our chart here. Okay, so first I'm going to draw a line pointing towards the star, which our smartphone is telling us it's oriented at 77 degrees. Okay, and then remember it told us that we were 40.5 nautical miles away. So what I do is I go the opposite direction by 40.5 miles, and then I draw a line there. And so bingo, that is the line of position. So we now know that we are somewhere on this line. We might be here, we might be here. And by the way, this line extends all the way out. So we could be anywhere on that line, but we know we're definitely not where we thought we were. Does that answer your question? Okay. So now remember, this line is actually a great big circle.
Wait. So question. So I understand that if Jupiter is 77 degrees away and we draw a line that way and we reverse the line, that's our line.
Yeah.
But what's the 40.5 seems remarkably specific.
Yeah, well, it's not a coincidence that it's so specific. I mean, basically, the way it works is that when we measured the altitude of Jupiter, then we put that into our smartphone, and the phone was then able to calculate what our zenith angle was, and the phone knows where Jupiter is located. And when I say Jupiter, I mean the geographic position of Jupiter. Okay, so the phone knows that at the instant that we measured Jupiter, the geographic position was at this point right here. And once it calculates our zenith angle, it then knows what our real true distance is from that geographic position.
Okay, I think I figured out what confused me. Can you go back to that real quick?
Yeah. Okay.
Okay, so that's our estimated position, and we're not there. We're 40.5 miles away from that.
Right.
But then we've got that line of position that goes up and down. How do we know that line goes in that direction as opposed to
okay.
any other direction?
Well, because we know that Jupiter is in this direction.
So just at a 90-degree angle to that?
Yeah, a 90-degree angle to that.
Okay.
That's it exactly.
Okay, got it, I think.
All right. Okay, so the smartphone knows where we told it we thought we were. The smartphone knows where Jupiter's geographic position is. The smartphone calculates the difference between where we told it we thought we were and where Jupiter's geographic position is. And then using the zenith angle that it gets from the sextant, the smartphone then calculates what is the real true distance from Jupiter's geographic position. And it finds out that the real true distance is 40.5 miles bigger than the distance based on our estimated position.
What if it was 40.5 miles the other way?
Then it would tell us that instead of being 40.5 miles away, it would tell us that it's 40.5 miles towards.
Oh.
And so in that case, then we would draw the line of position right here.
45 toward. Oh, okay.
Okay. All right. Now, for what you guys are going to do tonight, you don't need to do any of this. The smartphone is going to do it all for you. But starting on night 3 of the class, we are going to do this ourselves. Okay. But for tonight, the smartphone does it all for you. We're just learning what it is that the smartphone does. Okay. So we now have one line of position, but we need to do better. Okay. So now I'm going to go through this next part here really fast. You guys realize that what we do better is we're now going to measure a different celestial object. And so in the problem number 18, which by the way, this is also a homework assignment for you guys to do, is problem number 18. It says here that the second object that we measured was a star named Rigel Centaurus. So we're going to go through this exact same process. We're going to tell it that we measured Rigel Centaurus. We're going to tell it that this was our position. We're going to tell it what our sextant reading was, and we're going to tell it what time it was, and then we're going to calculate an intercept just like we did before. And so we're going to get a different number this time, and a different, and by the way, Zn, this is Zn that you see right here. This is the bearing. Okay, so if we wanted to point at the star, we would point at a bearing of 148. Okay, so what we can do now is we can use this information to get another line of position. And by the way, let me go back to here. This time you'll notice that the number that we get from the iPhone agrees very well with the number that we get from the other tool. Now, this time I was using a Palm Pilot. There's a whole bunch of different tools throughout the years, but you'll notice we're getting much better agreement now between the two tools. And the reason we're getting better agreement is because we're measuring a star, not a planet. And so the algorithms are able to calculate the positions of the planets, of the stars more precisely. Okay, so let's see what we do now. Okay, so we know that Rigel Centaurus, at least the smartphone knows that Rigel Centaurus is at a bearing of 148 degrees. So this dashed line that you see here is pointing towards Rigel Centaurus. And the smartphone does the math using the sextant numbers. And this time it finds that it's 50.1 miles. And again, it's away, not towards. So then what the smartphone knows that it needs to do, it needs to go in the opposite direction from Rigel Centaurus, a distance of 50.1 miles, and then draw a line there that's 90 degrees, and bingo. We now have two lines of position, so we now know where we are. Give me thumbs if this makes sense. Okay, and okay, good. All right, so this is where we are. Where are we? Okay, remember that there's always going to be error. And so you never want to just have two lines of position. You want to have a third because you want to triangulate it and you want to see is the triangle that you get, is it a big triangle or a small triangle? So we're going to do a third object. And in problem number 18, which is a homework assignment for you, the third object is going to be the moon. Okay, so then what we're going to do then is we're going to measure the moon, and now because the moon is not a small dot, it's a big circle. What we're going to do is we're either going to measure the altitude of the lower limb of the moon, which is the bottom part of the circle. We could measure the upper part if we wanted, but so what we're going to do is we're going to measure how many degrees is it from the horizon to the bottom edge of the moon, and we're going to put that into the smartphone, and the smartphone is going to calculate an app, and it's going to give us the exact same thing that it did before. It is going to tell us how far it is to the line of position, and when we now in this case it's towards. So in this case, it finds out that we're actually closer to the moon than our assumed position was, and by 47.1 miles. And so when we draw it, bingo, there is our triangle of position. Okay, so we are somewhere in that triangle. Now, in this case, this is a pretty big triangle. In fact, when you do this for real, if your triangle actually worked out to be this big, then that would not be good. That's too big of a triangle. So hopefully in real life, your triangle is going to be a little bit bigger than that, a little smaller than that. But also there's another thing that's not optimum about this triangle. A long skinny triangle is not really the best. In fact, let me go back. Okay. If you choose your stars wisely, what you should do is you should pick one star and okay, So you measure one star, and then ideally you turn 60 degrees either to the right or to the left, and hopefully there's a star located at that 60-degree point, and then you can measure that. And then turn another 60 degrees, or go over this way 60 degrees. So if you go over in increments of 60 degrees, then when you do your triangle, what you're going to find is instead of having a long skinny triangle, you'll have a nice, reasonably equilateral triangle. Okay, so this is the preferred shape of your triangle. But I got to be honest, quite often you don't have that luxury. Many times you're going to be out on the ocean and you're going to want to measure some stars, and there's going to be clouds. And so you're not going to be able to be choosy about what stars you get. You're going to have to take whatever stars you can see through the clouds. So there are going to be lots of times when you're going to have this non-optimum long skinny triangle. You're going to have that a lot. So you just take what you can get.
Question.
Yeah.
You're also on a boat
Uh-huh.
that's going up and down.
Yes.
So if you have your sextant in your hand and you're going up and down like that, you got a star that's going up and down. And
yeah, we're going to talk about that in great detail next week. It turns out it's not as bad as you might fear, because you are going up and down together with the sextant, and the horizon is so far away that this up-down motion turns out not to be as big of a problem as you would fear that it would be.
okay.
And we'll talk a lot more about that next time we meet. Okay, so give me thumbs on, tell me. So what you've just seen is how you put the numbers into the smartphone. So you're going to do this on two separate homework problems. One is you're going to take the numbers from problem number 18 and put them in the smartphone and see what you get. The other one is you're going to take the numbers that you get with the protractor, and you're going to put those numbers into the smartphone, and you're going to see what you get. So give me thumbs if you think that you know how to use the smartphone app to calculate what you need to calculate. Okay, Alex, how about you? Kind of iffy? Okay. All right, well, everything we're doing is being recorded, so you can go back and see it again. Okay, so we're pretty much done with the main meat here. Let's see. The different smartphone apps have different ways of maybe showing you how big the triangle is. Some on the Celestial app, it will draw the triangle for you. So if you want to see what the triangle looks like, it'll draw that. If you are on the Android app, it works a little differently. So if you're using the Android app, when you do the homework, you are not going to want to use the education tools. You're going to want to use the real thing. So what we just did was we used the education tools in order to figure out what's going on. But if you're using an Android, then when you do problem number 18 and when you do your protractor problem, what you're going to want to do is you're going to want to use this button right here. And let me just talk through this really quickly, just because I know there is one person who couldn't be here tonight, who's going to be watching this this recording, and he has an Android. So let me just show you really quickly how it works on an Android. Okay. So what you're going to do there is you're going to enter the numbers into the screen here. The first thing you do on the Android is you enter what are called the parameters. So that's the day and time. And if you're moving at any appreciable speed, the app needs to know what direction you're moving and how fast you're moving. And then you're going to put in your dead reckoning position. And so all of this, you just enter it once, and then you never have to change that again. And then what you're going to do is you're going to go in. It'll ask you if you want help planning your sites. If you would like to have a star map, it'll give you a map. But if you don't need help planning your sites, you can just skip that. And then this is where you're going to enter in all the numbers for Jupiter and Rigel Centaurus and the moon. Make sure that every time you enter one of them in, you save the observation. Yeah, otherwise, if you don't hit save, it'll lose it. Okay. And then once you've got all three of them entered in, then what you're going to do is you're going to move on to where it says fix. And then it's going to ask you what time do you want the fix for. Now, if you're not moving, then this doesn't really matter. But if you are moving at any appreciable speed, then you give it a time and it'll tell you where you are at that time. And then when you calculate it, it'll tell you where it is. And then if you want to see the triangle, here's a neat thing. I really like the Android app so much better. It draws a little globe here. And so what you can see are the three circles of position. And so it shows you this is where you are. And now you have the option of doing the globe projection, or if you want, you can do what's called Mercator projection. And if you do this, then you can zoom in. You know, you go in with two fingers and you know, like zooming in the way it works on a smartphone, and it'll draw the triangle for you here. So this is a great thing to do, is take a look at your triangle and get an idea for how big is the triangle, and is it a long skinny triangle or is it an equilateral triangle? That's worth looking at. Okay, so enough for the new stuff. Let's talk about your homework. Homework assignment number 1. I want you guys to take a protractor and rig it up with a weighted string. And I recommend you put a straw on the top, although you don't really have to, but it makes it a little bit easier to do it. And then I want you to go outside either tonight or sometime before we meet again. I want you to go out and find at least 3 stars, preferably more. The smartphone can handle as many stars as you want. If you want to measure 10 different stars and average them all out, that's a great way to improve the accuracy in your final results. So use a protractor, get a bunch of numbers, put them into your smartphone, and find out what your latitude and longitude are. Now, because a protractor is an extremely crude way of measuring angles, don't be surprised if your latitude and longitude is off by as much as 100 miles. It's not a fault of the smartphone, it's a fault of your measurement tool. If you want to get better results, you need to use a better measurement tool. And when we meet next week, we'll learn how to use a better measurement tool. I mean, I think considering the crudeness of this tool, the fact that it can get within 100 miles is actually pretty amazing, I think. Okay, but then homework assignment number 2, that's problem number 18. And so this is where we're going to put in some accurate numbers that we measured using a sextant. I'm going to put these into the smartphone, and let's see if we can get the fix that matches what I got. Now, answers are in the workbook. If you look in the back of the workbook, you'll see that there are answers. In fact, on page 64, you'll see I calculated this using a whole bunch of different tools. There's like 6 different tools. The Android, when I made this workbook up several years ago, the Astro calculator was not available at that time. So you're not going to see a number in there for the Astro calculator, but you will see the numbers here for these other tools. Here are the numbers for the Astro calculator. So when you take problem number 18 and you put it into the Android app, hopefully this is the number that you get. Now, most of you guys are on the iPhone, so the number that you guys get should be this one. Now it says here Android, but I've quit using it for Android. It used to be available on the Android, but not anymore. But it's now, so this one right here, this is the one that you guys will hopefully get as your answer when you put it in for your homework assignment. Okay. All right, let's see. Now, there are a couple of other things that you could do if you think that you need a review of how does land-based navigation work. So in the workbook, I have a whole bunch of review problems, problems 1 through 9 and 14 through 17. I'd like you to at least look at them. Now, some of you might look at it and say, oh, I understand that. I don't need to waste time doing it. If that's the case, then fine. Okay. But at least look at them and convince yourself that you know how to do them. Now, don't do problems 10 through 13. We're going to be talking about those next time we meet. Okay, so I see that Keith here is asking, why is it called dead reckoning? Well, it's called DED reckoning because that's short for deducted. But actually, if you want to spell it DEAD, that's probably not too far off. Because if you sail around the world relying simply on dead reckoning, DEAD is what you're going to end up as. So maybe that's a good way to answer that question there. Okay, so let's see. Anything else that we need to talk about here? I think that's it. How are we doing for time here? It's not bad. Okay. All right, so in fact, wow, that's perfect. It's 9:01. Are there any questions? Good.
Are there
No,
any?
thanks, Douglas.
Okay.
Are there any calculation programs you know of that are, online?
Yeah. You mean that you can run on a regular computer?
Uh-huh.
Yeah. I haven't looked in recent years, but one of them, this one right here, the bottom one on the list here, let me turn on. Okay. This one called Navigator. That's the name of the program that I used to use on a PC. And in fact, this screen right here, I think is a screenshot from that software. So this is the one that I played with many years ago called Navigator. I don't know if it's still available, but I'm sure there's a ton of them that you can get.
Okay. I'll probably play around and find some. If I find anything, I'll let the class know.
Okay, very good. Any other questions? Now, Alex typed in something about 20 minutes ago that I didn't comment on at the time, but yeah, planet comes from the Greek word wanderer because that's what the planets did. You're absolutely right. They wander among the rest of the stars. Yeah. Okay, well, if there's no more questions, then I'll go ahead and end the session. And I'll plan to see you guys next Thursday at 7 o'clock Utah time.
Thanks.
Thank you so much.
My pleasure.
Thanks,
See you guys
Doug.
later.
Have a good night.
Good night.